Number 7 is quite a nice problem involving many elements of the class that we've been talking about, including potential and capacitors and things. A lot of steps in this one. Let's see if we can make some progress on it here. What it has is a circuit like this with an arrangement of capacitors. There's a 100-volt battery here, and the switch is initially over here in position A. And when it's in position A, you can see that there's sort of a charging circuit going on. Battery charge from this battery here can flow off onto this capacitor plate, charging this plate to be positive, this one to be negative, and the capacitor will eventually become fully charged. Then what happens after that has gone on for a while, the switch over here is then rotated to the other position, position B, so the switch is sort of going over here like this, so no longer would the battery be in the circuit at all, but you have a fully charged capacitor now talking to two completely empty capacitors. And the problem asks various questions like, for instance, what are the charges, the final charges on capacitor 1, 2, and 3, say, a long time after switch B has been closed? Let's just sort of attack this problem and see what we can come up with here. This is a 15 microfarad capacitor, 20 microfarad, and 30 microfarad just sitting in there ready to go. Probably one of the first things you could calculate then is, well, how much charge ends up being put on capacitor number 1 when the switch is in position A. That comes very simply from the core capacitor equation here, that Q is equal to CV. So if I know it's a 15 microfarad capacitor, I can be 15 times 10 to the minus 6. There's my 15 microfarads, and it's been charged up to 100 volts. And if I do this here, I'll get the Q on capacitor 1 right there to be something like 1500 microcoulombs. So there's the first result for you right here. So when this capacitor is fully charged up, it holds 1500 microcoulombs of charge. Okay. Next step in the problem is, okay, so fine, so let's get this switch over into part B, position B, pardon me. So what we have in this case here is capacitor 1 sitting here, completely charged up, all the way up to 1500 microcoulombs, sitting here like this. And the charge now is going to distribute itself across these other two capacitors, say capacitor 2 and 3 now. This is sort of the after the switch is in position B circuit that, say, you would want to analyze here. So the question, homework problem asks then, how much charge ends up on capacitor 1 and how much charge ends up on capacitor 2 and 3, and say, what is the voltage across all of them? So let's just get right on that then. Okay, so we'll just start analyzing this circuit then. Okay, so what we know for sure, though, just sort of maybe with common sense or conservation of charge or any way you like to think about it here, is that if there's 1500 microcoulombs of charge here, then there's 1500 microcoulombs that will get redistributed across all the capacitors. So the 1500 microcoulombs will be the total charge that ends up on this capacitor, this one, and this one when everything is settled down or sort of reaches some equilibrium. So one of the first things I do then is I'll look at these two capacitors here, and I'd realize that they are in series, and they can be combined into series the way we discussed in class, into one big capacitor like this, and the series combination then would be a 12 microfarad capacitor. So if I combined a 2 and a 3 microfarad capacitor in series, the sum total capacitance would be 12 microfarads. Thus, this circuit, once again, can be drawn something like this. Here's my charged up capacitor like this. Here's the series combination of them here. And so now what I'm left with here is this is still the 15 microfarad capacitor over here. This is a 12 microfarad capacitor. And I know that this one has been fully charged to 1500 microcoulombs, my original calculation. So the question is, how does this 1500 microcoulombs distribute itself among both capacitors in the problem? Well, what I know then is that when I'm all done, the charge on the 15 microfarad capacitor, this one here, plus whatever charge happens to make it on the, I'll just sort of denote this here, onto the 2-3 combination right here, this capacitor right here, must equal to 1500 microcoulombs here. You can think about it as conservation of charge or whatever, but you have the 1500 to deal with, and that'll get redistributed among the original capacitor and the combination, the 2-3 one right there. So what I can do now is apply a bit of physics and look at the circuit here. And I notice that the top plate here is connected to the top plate over here, and the bottom plate here is connected to the bottom plate over here. What that means is, lo and behold, that these two capacitors here are at the same potential difference. So I put a voltmeter right here and right here. The voltage I would get right here would be the same for both capacitors. So having the same voltage across these capacitors is a key step, and that's a hard thing for you to sort of realize or know. You have to sort of apply a lot of intuition to figure that out, but it's true. Now what I can do is I can use my core capacitor equation that says that Q is equal to CV. This is the definition of capacitance. I'm just going to eliminate these Q's in terms of this here. So the C here will be the capacitance of the 15 microfarad capacitor, which is 15 microfarads, times the voltage across it, plus the capacitance across the 12 microfarad capacitor, which is 12 microfarads, times the voltage across it. This is the key thing here. The voltage across them are the same. So I'm just writing a V in both cases here. All that's equal to 1500 microcoulombs. So look at that. I have an equation I can solve for the potential difference across both capacitors. Remembering again, this number here will be 15 microfarads here. this number here will be 12 microfarads. And I can solve this and get that the potential across both of those capacitors is 55.5 volts. There's the first result in the problem. So again, what that means is that when the system has settled down, the potential difference across the original capacitor and the 12 microfarad combination capacitor is 55.5 volts. Alternatively, you can also think about it this way. When everything is settled down, the potential across this capacitor will be 55.5 volts, and the potential across these two capacitors here will be 55.5 volts, because this one here is these two in combination. So if the potential difference across this one is 55.5, the potential difference across these two will also be 55.5, and we'll use that when we try to wrap the problem up in the end. So I can now just start making some of the answers that are requested by this problem start falling out in the following way here. Let me make a little room here. So the first thing we can do is figure out how much charge is going to be on the 15 microfarad capacitor. We know its capacitance is 15 microfarad. We know the voltage across is 55.5. So I can tell you what the charge is. So the charge on a 15 microfarad capacitor is going to be 15 times 10 to the minus 6. There's 15 microfarads times 55.5. So the charge on the 15 microfarad capacitor is going to be 833 microcoulombs. There's your first answer right there. So you have the charge across it, you have the potential across it. That should complete one of the first answers. Okay. Now we're going to continue on with the other two. See, link of those things will work out here in the remaining board space that we have left here. I think we can do it here. What I'd like to do now is figure out how much charge flows across the combination, the 12 microfarad combination capacitor. I can do that with the capacitance equation again. So in other words, the charge that is available for the 12 microfarad combination capacitor, or the charge that eventually goes across capacitors 2 and 3, same system here, is equal to the capacitance of the system times the voltage across it by the definition of capacitance here. Q is equal to CV. We're still using that one right there. So onwards then, CV, the capacitance of the system here, is the 12 microfarads, 12 times 10 to the minus 6. The voltage across it is 55.5 volts. So the charge that gets distributed across both of those capacitors in combination then is 666 microcoulombs. This is how much charge flows onto this one capacitor. But since this one capacitor came from these in combination here, it's also the amount of charge that is available for these two capacitors as well. So there's another answer for you right there. Maybe not directly for the problem, but it's one of the answers along the way. So we have this now, and now you have to apply a little bit of physical insight here. Where again did this capacitor come from that got the 666 microcoulombs across it? Well, it came from these two in series. Now remember, the definition of series here, I'll just sort of jot it on here. The definition of series here is that Q is the same. That's the definition of series for capacitors. Capacitors in series have the same charge on them. Same charge on them. Q is the same. So if this capacitor right here got charged up to 666 microcoulombs, that is also the amount of charge that makes it onto either one of these here, because they are in series here. This 666 microcoulombs is how much is on 2 and 3, and that's a key element for getting this problem to solve out here. So I'm going to make a little bit of room here. It looks like I'm running out of room. So a little bit of erasing in there. Now I've got a little bit more room for myself. So what we've just discussed or decided here is that this capacitor right here will get 666 microcoulombs on it, as will this one right here, because that's the definition of series. In series, the charges are the same. So now I'm free then to go figure out some things about capacitor 2 right here. In particular, the charge on capacitor 2 is equal to the capacitance of capacitor 2 times the voltage across the capacitor 2 here. That's the definition of capacitance once again. And I know how much charge goes on capacitor 2. That's going to be the 666 microcoulombs. Of course, I know the capacitance of capacitor 2 there. It's a 20 microfarad capacitor. 20 times 10 to the minus 6 times the voltage across capacitor 2 there. And if I solve for that, the voltage across capacitor 2 then is going to be 33 volts. There's one of the answers for you right there. 666 microcoulombs charge on it. That's the capacitance. That must be the voltage across there. So there's two big answers there for capacitor number 2. It's going to get 666 microcoulombs of charge and have 33 volts across it. This is all the information you need for the 20 microfarad capacitor. That's going to be your answer in there. Okay? And now we can just apply the same thing for capacitor 3 here, which is a 30 microfarad capacitor. Do the same sort of analysis here. charge on capacitor 3 is going to be equal to the capacitance of capacitor 3 times the voltage across capacitor 3 here. I know everything except the voltage, so the charge on is going to be the 666 microcoulombs. The capacitance of capacitor 3 here is 30 times 10 to the minus 6 farads. There's my 30 microfarads in there, and the voltage across it V3. That's what I'd like to solve for. So the voltage across this capacitor right here, capacitor number 3, the 30 microfarad capacitor, then can be found by solving this equation here, and I get something like 22 volts. So that should complete my answer set for this. There's the 22 volts for capacitor 3 here, so all of these things right here apply to the 30 microfarad capacitor. So there's the problem for you right there. I have the charge and volts across capacitor 2 and 3, and I should be set.